Hello, everyone. If you remember, I promised you to talk about the complicated behavior of the rattleback. So, a few days ago, I published a short video about how rattleback behaves, right? If you spin it in one direction, it is fine with it. If you spin it in the other direction, it stops, it oscillates, it does a pitch oscillation, and then goes back in the direction it prefers. So the mathematical formulation of that and simulation of that is found in some paper. You can find it in different papers. The one that is my reference today is this one, Global Motion of the Celt by V.P.H. Zhuravlev, I guess, and D.M. Klimov. And by the way, the rattleback in many publications is called celt. Okay, so rattleback is celt, they are the same name, basically for the same object. Now here in this paper, the model, as you can see, is a half ellipsoid. And you might say, where are those asymmetries? Remember, we have some cut here and some cut there. So that is not shown here. Instead, it is modeled, we'll see, by some angle later we introduce called D, which is the angle between the principal axis of this ellipsoid, okay, and then the theoretical ellipsoid major axis. So basically, if it's an ellipsoid with no cuts, no asymmetry, then the principal axes are going to be what? The principal axes are going to be this axis, right? This axis, and the one in the upright direction, this guy. But if there is asymmetry involved, then these axes will be rotated. The Z1 is going to stay, but these two will rotate, correct? So, for instance, they might rotate to something like this. One of them becomes this, and the other one becomes that. Okay, so this angle here, this rotation angle here, is shown by parameter D, and that depends on how much you cut in either direction. And you can see that this D, for instance, here, this angle D from the theoretical one to actual one in this case is basically clockwise, and you might spin it what? Counterclockwise. So they are in the opposite direction, or you might cut the opposite way, right? So you might basically do the cuts here and here. So now your axes are like this and this. So your rotation for omega and this angle D are now in the same direction. So based on this rotation angle and this theta, whether they are in the same direction or in the opposite direction, you get those two different types of what? Behaviors, or those two different types of rattleback. One of them only prefers to go clockwise like this. The other one, that the cut is in this direction, that likes to go counterclockwise. Okay, once you spin it in the opposite direction of D, you're going to get that backward motion, stopping and going back. So mathematical definition is what in this case, or formulas? So there are three forces acting on this celt or rattleback. One is the mg at the centroid G here. The two other forces is, one is the friction force F, and then the normal force N, both applied at the contact point P of the rattleback with this plane XY. Okay, yeah. So we have three forces, and here the vector from the geometry centroid of the ideal ellipsoid O to the contact point is shown by vector R, and the vector from the geometry center O to the actual centroid G is shown by vector K. So K is G to O or O to G, and R is from O to P. Okay, yeah? So one is this vector, as you can see. The other one is this vector. And J of G here is the tensor of the inertia of the body, which has three major inertias, A, B, and C, capital A, B, C. So it's a diagonal matrix. N here is a scalar. That is, as I said, shows the normal force. The direction for N is shown by lambda here in our equations. F here is the sliding force, and it is a vector, so I need to use a bold font for it. And capital I here is the direction parallel to the inertial z-axis at the contact point. Okay? So here we also have two frames, capital XYZ, which is the inertial frame, as well as what? Small xyz, which is attached to the body. So this is the body attached frame. And the capital XYZ, as I said, is what? This is your inertial frame. So, if velocity of the centroid of the object G is shown by vector V, mass of the object by M, and the angular velocity vector of this rattleback is shown by omega, the equations of motion for the rattleback are these two, based on Euler-Lagrange equation. The first one is sum of the forces equals m times a plus omega cross v dot. Now, what is that? So this is a, right? This is m times a. Why do you have this extra term? Because you are writing the equations in the body attached frame. And in the body attached frame, this mv, this linear momentum, is written along this small xyz axis, which themselves are rotating. So this linear momentum mv has two varying conditions, I would say. One is its magnitude, the other one is the direction of it, because of the direction of what? The direction of the unit vector. So this one is the magnitude and the direction, actually. For V, this is the change of direction for the axis of the body attached frame, omega cross mv. Okay, so this whole total thing equals sum of the forces. And here the mg force in the negative I direction is applied, N is applied in the lambda. Now in this case, lambda might be the same as I, not in general. And of course this F force, which is shown with negative F. And then this negative is just to show the opposing the motion. And in the for the rotation, we have I times omega dot, or I times alpha, plus again this angular momentum jg omega. It has a variation due to these three axes being rotating, and that is omega cross that. So this whole thing equals summation of the torques or moments about the centroid. So here there are two forces that create a moment about centroid, F and N. What are their radius, or what are their arms? So for centroid, with respect to P, the vector is this guy, this one here in blue. And what is that vector? If you look at the definition of K and R, you can see that it's K plus R. That's why you see here what? K plus R, which is cross multiplied by I and F. Now why I? Because I here is the direction of N. As I said, in this case, lambda and I are the same thing. And F here is a vector entirely, so this whole thing is the R of P with respect to G, right? Cross that, and again this is R of P with respect to G. And N times I is the normal force. So these two are the translation and rotation equations of motion. The last one here is, what is this? This is d of I with respect to dt in the inertial frame, which is equal to d of I with respect to dt here. This one is in the body attached frame. Remember, everything is written in the body attached frame. So this is small xyz plus, of course, because the, again, unit vectors here are changing for xyz, and this capital I is written in a small xyz, you have to add plus I omega equals 0. So that means the vector I in the inertial frame does not change, okay? So this is a geometry condition. Now also, the contact point here does slide on the xy plane, but it does not get off the plane. So the velocity of the contact point, which is v plus omega r, correct? Omega cross r. V here is, remember, v of g plus omega cross r, and r is this vector. So that is velocity of point P dot I. Projection of that in the vertical direction should be 0. That means point P will never leave the surface. So these are the two equations that we have subjected to these two conditions, this one and this one here. So now let me do a little bit fast cleaning. So see how many equations so far we have. If we go ahead and number them, that's equation 1, this is equation 2, this is equation 3, that is equation 4. Now for the dry friction force F, here we use the Hertz model or Hertz law, and the Hertz law assumes that the contact of the object with the surface is a very small contact, and the radius of that contact spot is rho. So you know, whenever two objects come into contact, the contact is not really a single point. It's theoretically a single point, but in practice, if you zoom into this contact region, you have a small circle of touch, and the radius of that is what? Rho, but this is a very small region compared to what? The physical object, of course. So if rho is the radius of that, and f, small f here, is the coefficient of kinetic friction, so this f is the same as mu in our dynamics notations, then based on the Hertz law, which is basically forces between contacting surfaces, so here assuming that you have a spherical, or in this case ellipsoid surface in contact with another one, the F force can be approximated by this formula, where F is again the coefficient of kinetic friction, N is that normal force, V plus omega cross R, if you remember, that's the velocity of the contact point, right? And this 8 over 3 pi again comes from this Hertz law assumption, and rho, omega, and I are all given. So you see that this friction force not only depends on the normal force, not only depends on the kinetic friction coefficient, it also does depend on the sliding velocity and the spin. Okay, and in general, if you watched one of my videos in playlist statics where I talked about kinetic friction, you know that in reality, kinetic friction Fk, right, which is mu k times n in our theory, that's not reality. It's not just depending on n. That actually does depend on the relative velocity. And you can show that as well relative velocity is increasing, this friction is dropping a little bit. So here you can see that effect. Okay, and so this is going to be what? This is going to be our equation number 5 here. So let's go ahead and write it down. Okay, so now do we have enough equations to solve for v's and omega? Especially omega is the one that we care about, the rotations of the object and the components of that, omega 1, 2, and 3. So do we have enough equations here? Well, if you look, the equations that we ultimately have to have are 1 and 2. These are the ones that give us differential equations for v and omega, right? So anything else in 1 and 2 that is not known, we have to have an equation for it. So our unknowns are v and omega, it's I, it's n, and it's r. Okay, yeah? So we need to have a bunch of relations here. What about f? Well, if you look at f, f here is what? F here is given in terms of v and omega and r and n. Since these are already counted as unknowns, so I'm not going to count f as an extra unknown here. Okay, yeah? So now, as I said, so f, we say, let's say we know this as something, as functions of something else. So now we need to have what? We need to have 3 extra relations to get rid of I, n, and r. How many relations do we have? One of them is 3, which is about I. One of them is 4, which relates r and I. Okay? And I need one more because remember, I have 5 unknowns in 1 and 2. If we get rid of f through equation 5, I still have 5 unknowns. So I have 3 and 4. I need one more equation, so I have 5 equations and 5 unknowns. Or if I count f, 6 equations and 6 unknowns. Okay? Yeah? So I need one extra equation. That comes from the geometry here. And through geometry of this ellipsoid, I can relate vector r to vector I directly without any other parameter in between. And you can show that mathematically r and I as well as lambda are related by what? R is negative of a matrix R inverse times I divided by square root of, here this is a dot product. So this is a dot product of lambda and R inverse dot I, where this R inverse matrix is given by, here you see this 3 by 3 matrix. Okay, what are the parameters in this matrix? We have A, B, C, and D here. What is A, B, C? What is D? So A, B, and C are what? Are the ellipsoid principal axis. These are those numbers, right? A, B, these are the semi-major, semi-minor, and for the height, these are those 3 values for the ellipsoid principal axis. So they are of units length, and here we assume that A bigger than B bigger than C. And D here is that angle that I initially mentioned, the angle of asymmetry, the angle which is between what? Between the principal axis of inertia and the actual, the theoretical ellipsoid axes, right? Yeah? So you have the actual ones, which are due to asymmetry, and the theoretical ones, which are straight, passing through the endpoints. And this angle between them, if we call it D, and we plug in A, B, C, D, here we can get this our inverse matrix, plug it here, and this one, if we know I, it can directly give us R. So now if I call this equation 6, I got 6 equations and 6 unknowns. Of course, not necessarily so simple to simulate, but here in the paper, simulations are done. So N is considered to be mg, M is like 0.15 kilogram. The 3 major moments ABC that are used for this JG, remember these 3 ABCs are given by these numbers, 0.002, 0.0045, and 0.0006 kilogram meter squared. The 3 major dimensions ABC are given by 0.07, 0.016, and 0.01 meters. G is considered 10, you can go 9.8, the coefficient of friction 0.1, the radius of the contact region is 0.0012 meters, you see very small, and K3 here is considered 0, so we assume that we spin it basically perfectly vertical in the beginning. Velocities of the centroid are considered 1 and 2, 0, and the L here is basically JG times omega, the angular momentum. For the 1 and 2 direction are 0, for 3 direction is 1. So the only thing we have in the beginning is spin about a perfectly vertical direction. And if you look here, there are these 2 separate simulations. In case 1, the angle D and the component omega 3 of 0, they have opposite signs. So the Rattleback likes, let's say, to go, in this case, there are three curves. I don't know if you can easily see them. Let me zoom in, because in the paper they did not use any color. But if I want, let's see if I can use color myself, hopefully. So I can add some color for you. This is maybe too thick. This is your omega-3 in red. Okay, so omega-3 is in red, and then we have omega-1 and omega-2, and again, you have to look at the color. So one of them is like this bigger oscillation, like this, if you look at it. And the other one is this smaller oscillation that is underneath it. If you look at that, it looks like this. You see it? So one is the one with bigger magnitude of oscillation. The other one is this one with smaller magnitude of oscillation. And I'm not really sure which one is omega-1, which one is omega-2, because it didn't say anything. But let's say omega-2 is blue and, for instance, omega-1 is green. So one thing obvious is this. In the case that you started with these D and omega to have opposite signs, what happened to omega-3? You see, you started omega-3, in this case positive, which means counterclockwise. And then immediately after the start, you see it went from positive to now what? To negative. So means it stopped right here, it became 0 after a short time. And then immediately after that, it starts to go what? Started to go clockwise now. So here is counterclockwise, here it is clockwise. And then over time, due to friction, it slows down and wants to go back to 0. Yeah? So you see here, you can see the reversal of direction. But here is the case that they have the same sign. So the Rattleback wanted to spin counterclockwise, and you did spin it counterclockwise. So still, you started omega-3 what? You started omega-3 positive. And as you can see, it does not very fast reverses and goes to 0 and negative, and it just gradually slows down until it stops. Okay, you see that? So no reversing here. And the other important thing that I said you might want to enjoy is what? Look at omega-1 and omega-2. They have what in them? They have oscillations. Remember when we did the spinning of this Rattleback, right? When it stopped and reversed, you had this kind of oscillation, right? So you had this contact, this guy going up and down, and also it did actually a little bit in this direction as well, but this pitch direction was a big oscillation, and you clearly can see the oscillation for omega-2, right? You have big oscillations, and as the oscillation gets bigger magnitude, you hear that rattle sound, right, that you did in my short video. Okay, so hopefully here you at least see the mathematical foundation for the Rattleback. And there are so many papers, so many studies that try to explain this amazing behavior of this object that looks very simple, but because of some small asymmetry or that angle D, it does this amazing behavior. So this is our reference in this video, but there are so many other papers. Hopefully you enjoyed it, and I'll see you in the next video. Thank you.